Hello, statistics students. In the past, we've talked about describing a distribution using its center, shape, and spread. Today, we're going to talk about the center of distributions, the measures of central tendency. And the three initial ones that we're going to look at here are the mean, the median, and the mode. Now, the mean is just an average. The median is the number in the middle, or an average of the two numbers in the middle. And the mode is the number that occurs most often. So let's talk about these more in detail. To find the mean of a population, you add up all the x sub i's. Now that just means x sub 1, x sub 2, x sub 3. Those are just your data points. And that big sigma means add them all up and divide by big N. It's actually an uppercase nu, I believe. And that is how many data points are in the population. So that's just your regular formula for a mean, an average. And again, we're using the Greek letter mu because we're discussing a population parameter, and the Greek letter nu, again, because we're discussing a population parameter. If we want to look at a sample mean, we're going to use x bar, and it looks the same. We're still adding up all the data points and dividing by the number of data points. In other words, dividing by the sample size. So these are our two formulas for mean. Two things you need to know about the median. First, when you're given data, to find the median, you must put the data in numerical order. You must put it in order from smallest to largest. If you do not do this, bad things happen. The world comes to an end. It's like dividing by zero. You must put the numbers in order from smallest to largest. Then, take your number of data points, add 1 and divide by 2. So if you have an odd number of data points, let's say 15. 15 plus 1 is 16. 16 divided by 2 is 8. So your 8th data point is the median. If you have an even number of data points, say 12. 12 plus 1 is 13. 13 divided by 2 is 6.5. Then 6.5 tells you you take the average of the 6th and 7th data points when they are in order from smallest to largest. Let's take a look at an example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. They're in order from smallest to largest. 10 plus 1 is 11. 11 divided by 2 is 5.5. So I go to the 5th and 6th data points right there in the middle. I average the 5th and 6th data point. Well, they're both 8. So 8 is the median. Now, if 8 is the median, you say, well, half of the data points should be less than or equal to 8, and half of the data points should be greater than or equal to 8, and that's exactly what you get. The median, because it's in the middle here, this 8 belongs in the lower half of the data set. This 8 here, in fact, all three of these 8s, belong in the upper half of the data set. So 1, 2, 3, 4, 5 data points below the median. 1, 2, 3, 4, 5 data points above the median. And if you have an odd number of data points, like we have 11 data points here, 11 plus 1 is 12. 12 divided by 2 is 6. 1, 2, 3, 4, 5, 6. This data point is the median. It's not in the lower half or the upper half of the data. This data point isn't. But again, you can see that half of your data points are, at least the lower half of the data, these 5 are below 8, and these 5 are greater than or equal to 8. It's just that 8 is the median. It's the number in the middle. The mode is the number with the highest frequency. It's the number that occurs, the mode, or the number of the interval that occurs most often. Now, there may be no mode. In other words, every number occurs once. Or there may be more than one mode. In other words, the number 6 occurs 5 times, and the number 8 occurs 5 times, and everything else occurs less than that. Or maybe everything occurs 4 times. Whatever it is, there might be no mode or more than one mode. Sometimes in statistics, we see what we call a bimodal distribution. And a bimodal distribution looks like this. Let's say I'm measuring the height of adult Americans. And you see I'm going to get really small numbers out here. Then at 5'4", there's going to be a peak. And it's not going to go all the way down here like this is. It's going to stay up here a little bit. Then it's going to peak again here at 5'9", and then it's going to trail off. Answer to yourself, what is going on here? Why are there 2 peaks when we're measuring the height of adult Americans? And the answer is, when you see a bimodal distribution like this, oftentimes you're actually measuring 2 different populations at once. And obviously we're measuring men and women. Men average around 5'9", women average around 5'3", 5'4", and you're going to have tall women in here and shorter men in here, and that's why the curve doesn't go all the way down here to the previous lows, because you're getting some of the women and some of the men in here. So you're going to peak here with these women, then you're going to peak again with the men. So if you're measuring heights, you can't just look at adults. You have to look at biological sex. So that's a bimodal distribution. Let's take a look at different shapes of distributions. And somewhere here, I'm going to pause this recording because I forgot my book. And I'm back. Let's take a look at these shapes and discuss them. This distribution is symmetric. There's a line going through the middle, and it's a mirror image on either side. Now, in the real world, that will almost never happen, but if it's close enough, we can describe it as symmetric. And you'll notice that the mean, the median, and the mode are all the same here. This is a uniform distribution where every number in here has an equal occurrence. And the mean and the median are the same in this one, but there is no mode. Now this we call skew left. And what happens here is there's a peak, and you notice that this left tail going from the peak down here, this left tail is longer and more spread out than the right tail. This is left skewed. Now you'll notice that the mean and the median up here are the same. But you'll notice here that the mean has been pulled to the left in a left skewed distribution. And that's because, as we know, extreme values affect a mean. If you have a really small value, that's going to lower your average, your mean. If you have a really high value, that's going to increase your average. Well, you've got these really low values out here, so that drags the mean to the left more than it drags the median to the left. So this is skew left. And again, you have these high values out here that drag the mean more to the right than the median. So this one is a skew right distribution. And I would recommend taking a look at the information on page 73 of our current. Now this slide says for tomorrow, but it's going to be part of this same lesson. Gotta love the coronavirus giving us these long classes. So if you have this frequency distribution, and I wanted to find the mean of this distribution, you have 21s, 22 2s, 22 3s, etc. How would you do that? Well, what we would do here is I would say, well, I could just add up the number 1 20 times, or I could multiply 20 times 1. I could add up the number 2 22 times, or I could just go 22 times 2, etc. Anyway, I'm going to add up all the data points. So I've got almost 100 data points here, 20 something, 20 something, 20 something, about 90 something data points. And so I'm going to divide by whatever this adds up to, which I think is close to 90. So I can do a weighted mean, and we're weighting it because there aren't as many 5s as there are 2s. So I can't just go add up these 5 numbers and divide by 5. That would not give me the average of this distribution. I need to count the 2s a lot more than I count the 5s, because there's 2.5 times as many 2s. So we're weighting the mean more towards the 2s than we are the 5s. So you can see that by doing the sum, you do x times the frequency, all you're really doing is just adding up all the data points. I'm adding up all 20 ones. I'm adding up 1 20 times. I'm adding up 2 22 times. I'm adding all of those together and dividing by the frequency. And this would be an example of service ratings at a restaurant. You're rating them from 1 to 5. This would not be a good service score, by the way. So I've already introduced to you in a previous class the spreadsheet project we're going to do about smoking rates and taxes. So my first question is, maybe you want to pause the video and break out that data on smoking rates and taxes, smoking rates and taxes in the from the project. I'll wait while you put this on pause and go get that form. All right, I waited. So how would we calculate the average per pack tax for the county? I'm sorry, for the country. Can we just add up the tax rates and divide by 50, or if we include DC, 51? Is that reasonable? Okay, so now I'm going to say, I'm not going to give you the answer in this video. Please ask that question in class. Next, Kentucky has more people and a higher percentage of smokers than Wyoming does. If we're trying to find the average tax rate for the whole country, shouldn't Kentucky's tax rate have more influence in that average than Wyoming's should? Okay, ask me about those two questions in class. So let's take a look at a weighted mean. Now what we did in the last couple slides was the mean of a frequency distribution. You'll find that a weighted mean is the same thing. And that was what we were doing with Kentucky. We're actually weighting the average towards Kentucky over Wyoming, because Kentucky has more people and more smokers. But let's look at an example that you're much more familiar with, and that is calculating your grades. Here's how I calculate your grades in this course. I take your test average, which hopefully will be 90-something%. And I weight that at 25% of your total grade. Quizzes are 25% of your grade, etc. So your average, which is your grade, your overall grade, is I take your score times its weight, and then I divide by the total or the sum of the weights. Well, the sum of the weights is 100% or 1.0. So I take your test average times 0.25 plus, that's what sigma means, your quiz average times 0.25. So your average times the weight, plus your project score times 20%, etc. Add all those up and divide by the sigma of the sum of the weights. It's doing the exact same thing as we did with the frequency distribution average. It's just that we're looking at it in a different way. Instead of having 21s and 22 2s and 22 3s, I'm thinking of it, we're going to take, if we're going to piece together a pie and of that grade, 25% of your grade is going to be this number, and 25% is going to be your test number. So again, this is the formula for finding a weighted mean. If we want to find the mean of a frequency distribution, you'll notice it really is the same formula, except we're using the frequency instead of a weight. There's two different ways of looking at the same process. But let's go back to that frequency distribution. What if our frequency distribution looks like this? All of a sudden now, I don't know how many 11s or 12s there are. I only know that there are 20 total, but I don't know, are they 11s or 12s? I don't know if how many 13s there are and how many 14s there are. I only know that there are 25 total of those. So if I want to estimate or approximate, we're actually going to approximate the mean of this distribution, what we need to do is we're going to do the mean of a frequency distribution, but our data points, I don't have 11s and 12s anymore, I just have this interval. So I have to do the midpoint. So between 11 and 13, I have 20, that's an average of 12. So I would go 12 times 20. I'd go 14 times 25, etc. And then I would add up all these ends, or you can also look at the ends as the sum of the frequencies. So again, if I don't know, if I'm just giving these intervals, I have to use, my data point here is going to be the midpoint of the interval times the frequency of the interval. And that will give me an approximation of the mean. We've talked previously that when we analyze a distribution, we want to look at shape, center, and spread. Like, for instance, these are both normal curves, the bell-shaped curve, but this black curve here, well, actually, they're both normal curves, and they both have exactly the same center. But the black curve is shorter and more spread out than the purple curve. The purple curve really peaks here, and it's not spread out very much. So we want to describe the shape, center, and spread, because you can see now that shape and center are not satisfactory. These two curves have the same shape and center, but they're obviously not the same curve. So we're also going to look at spread. And what we talked about today was the center. We did a little bit on shape, and we talked about primarily the center, different ways of finding an average, or a median, or a mode. Now here's some information that we'll eventually need. When I say tomorrow, I don't know if it's going to be tomorrow or not, here in Corona time. So if we're looking at population variables, if we're looking at a mean, we use mu. If we're looking at a population size, we use, I might call it big N, but it's actually an uppercase nu. It's a Greek letter that makes the N sound. If we're talking about variance, which is a measure of spread, we use this sigma shape. And the way I do it is I start here at this intersection point, go down and to the right, make the circle, and then keep going to the right to make a tail. So that's the lowercase sigma. We know the uppercase sigma kind of sort of looks like a capital E, and that's what we've been using for sum. But this lowercase sigma makes the S sound, measure of spread. And variance is sigma squared. You take the square root of variance and you get the standard D, sigma. So we're using Greek letters to describe these four quantities, these population parameters. Those same variables, When we want to calculate statistics, a population mean, we're going to use Roman or Latin letters. X, lowercase x, but we will actually do an X with a bar over the top. This is called X bar. A sample size is lowercase n. Sample variance. So if you take a sample of data, you take a sample from a population and you calculate the variance of that sample, that variance is written as S squared. And if you take the square root of that number, you get the standard dev, and that's S. Remember that the full name for this is standard deviation, but all the cool kids call it the standard dev. That's it for this lesson on measures of central tendency, with a little bit of preview on Greek and Roman letters for different parameters and statistics. That's all I've got. It's late in the afternoon. I'm calling it quits. Have a great day.